Hello YouTube! Today we're going to be talking about how to model the movement of both one and two objects if those objects are moving at a constant velocity. This is sort of one of the simplest situations that we'll be dealing with in this class, aside from, I guess, stuff that's not moving, which is complicated in its own fun way, actually. Um, yeah, let's dive in. So in particular today, again, just modeling how stuff's moving. If you're able to pick out the givens from a word problem, if you're able to set up your equations using that and then solve things out, you're in fantastic shape. If you can do it for one object but not two, that's honestly really good. And take the victories where you can. As you practice, hopefully you get more comfortable with how you do it with multiple objects as well. If you're in class, I do not expect you to be able to sort of do this in a day and then move on from it. We'll probably spend at least 2 days on this. So if you're watching along on YouTube, bear that in mind, I suppose. So the one example that we're really going to be going through today, and then we're going to do a second one just so that you can have another example. But honestly, if you want to stop after the first because you feel like you're in a good spot, that would be fine as well. Is that you and a friend are driving to New York. You start out 30 miles behind your friend and 120 miles from New York. You drive 70 miles per hour and your friend drives 60 miles per hour. So A, how long did it take for you to reach New York? B, how long did it take for you to catch up to your friend? And C, how long will you be waiting in New York for your friend? Now, for A, in theory, you could actually use average speed, average velocity in order to solve it. And this is something that we've pretty much already worked with. But I want to go into a way that's a little more applicable, more broadly. Well, actually, honestly, less broadly, but in this circumstance. So the equation for how something will travel at a constant velocity is that your position is going to be equal to your initial position where you started, x naught, plus vx, meaning the velocity in the x direction. This is the nomenclature from the AP Physics 1 sheet, so that's why I'm using it. If you just want to do v, that's fine, but be aware that especially when you have multiple directions of both x and y, or x, y, and z, it's really nice to actually get in the habit of including that x so that when you have to include the x, you're already doing it. And time, t. So variables for that are written right here. I actually do want to take a second to sort of derive this one in a sense, or show you where this comes from, which is pretty much just from our basic idea that if we take how far we go and we divide that by the amount of time it takes to do it, that'll give us roughly how far we went in each given unit of time, which is what velocity is. So if we start from our equation that velocity is equal to displacement over time, and do be a little careful with this one because this actually only works if it's a constant velocity or if it's the average velocity. Now, if it's a constant velocity, then the constant velocity will be the average velocity, which is part of why we can just call those the same thing here. But when we get to the parts where it is accelerating, where it is changing its velocity, you can't do this anymore, just as a heads up. Well, delta x is equal to our final position minus our initial position. And so if we take that and then rearrange it so it looks a little nicer, that'll bring us to this. So to do that, we multiply each side by the time, and that'll happen to the middle equation as well in order to conserve equivalence. And that'll give us that our, I'm flipping the order, our current position minus our initial position is going to be equal to our velocity times time. And then all we have to do is add our initial position to both sides, and we wind up with our equation. So that's where that comes from. Especially because this is probably the most straightforward derivation we have all year. Figured it would be good to make sure you get a chance to see it. So, actually using that equation, we've got a situation where we've got two people going to a place. I know that we're driving to New York. I start out 30 miles behind my friend and 120 miles from New York. So if I look at me and I look at the friend, I start out 210, I think I just said 120 miles away. My friend starts out 30 miles in front of me. I need to change the problem. I thought I fixed this last year, but I did not. The numbers aren't going to work out particularly well, but let's make it... no, I guess if we just double it, it actually should be fine. 420 miles. Yes, that should do it. And I'm going to need to change it here. And I'm going to need to change it here. Great. Sorry about that. Unfortunately, there's going to be a decent amount of this because I did not used to be as good about changing the things when they came up. Okay. So, we've got to update this. And the 30 miles should probably be different. This is not going to be... Well, this will work, or at least it'll come close to working. Okay. So, here's our setup. And in question A, we're being asked for the... Oh, actually, I should say that this person's going at a velocity. So velocity for your friend is 60 miles per hour. The velocity for me is 70 miles per hour. And my displacement for me is 420 miles. And there we go. So for A, how long will it take to reach New York? So if we look at our really only equation we have so far, especially our only equation that involves time, again, you could use the average velocity for this one, and that would probably make it a little easier. But I do want to practice with the newer equation. We know that our final position is going to equal our initial position plus velocity times time. So in this case, that'll be that the position that I'm in needs to equal the initial position that I'm at plus the velocity that I'm traveling at times the amount of time that it takes for me to get there. And so I'm basically just adding the subscript me to everything, so I know to be careful about which variable I'm using because there's going to be multiple initial positions, there's going to be multiple locations, there's going to be multiple times, and this sort of helps with that. So sorry, I'm blanking real hard right now. One of the big things for this is that we have displacement, we don't have the final position, and we don't have the initial position. And a big part of that is because positions are always relative to something, meaning I have to pick a location to be where I start. I have to pick a location, or specifically I have to pick a location to be 0. In this case, to me, it looks way easiest. The thing that looks the easiest is to take this location where I start, which is the furthest back one, and make that 0. No matter where you pick, you will get the right answers to the problem, as long as you do it right. Personally, I like picking the place all the way to the left because it stops there from being negative positions. But if you have something where, for example, they start in the same place, oftentimes that's a really convenient place to make x equals 0. So I'm going to say that this position is x equals 0, which means that anything that's here is 0. And what that lets me do is it lets me say that my initial position for me is 0. And my final position is 420 in front of that. So that means that my final position will be 420. What I can also do, although it's not going to matter for A, is set up for my friend who's 30 miles in front of that my initial position for my friend is going to be 30 in front. And my final position for my friend is going to be 420 in front of that. Which again isn't going to matter yet, but will eventually matter. So, solving this out, we're looking for the time. The one thing that I will say about plugging in numbers first, I don't like doing it unless it's a 0. If it's a 0, it tends to make the math a lot easier, and it tends to be a situation that can probably come up fairly often. So I will plug in the 0 here. I know that my initial position here is 0, so I don't have to worry about it, and it's like it's not there. Rewriting it out, I know that my position will now need to equal whatever velocity I'm traveling at times the amount of time I'm going for. And if I'm looking for the time, all I have to do is divide each side by that velocity, and that'll isolate the time. And so our final answer is going to be that the time it takes me to get there will be equal to the distance I'm going, or the end location, divided by the speed I'm going at, which in this specific case is going to be 420 divided by 70 miles and miles per hour, which I think is just going to be 7. I divided by 60 for some reason. It's going to be 6. So it takes us 6 hours to get there. And that's it for A. For B, it gets a little trickier because B is A, not asking us about how far we are from New York, and also additionally, sorry, I just realized I was going to mix A and B. Additionally, oh, that's exciting. B is additionally asking us about a second object. So this one's actually going to be a lot trickier, and we start to have to actually set up a system of 2 equations in order to solve for 2 objects. So the big way that we're going to do that is, first off, just knowing how to do it and when you can do it. This is specifically if you've got 2 objects at constant velocity for the second half. Although I guess that's the situation where it's most useful, or at least most straightforward. So the first way is to do a system of equations. Anytime you have the same number of equations and things you don't know, you can solve it. And it'll work if you set up a system. To set up a system of equations, you get multiple equations, in this case 2. You solve one of those equations for one of the unknowns in terms of the other. If you're not sure what that means, check out Unit 0. And then plug it into that first equation again, the other equation that you have, and that'll let you solve for that variable that you had solved in terms of for the first part. This is the way we're going to demo for this. Also going to demo a second way where we set up, where we think about the situation not as 2 separate objects moving at different speeds, but what it looks like for one of the objects, because from the perspective of one of them, well, I mean, it's not moving, right? And that's sort of thinking about if you have ever been in a train, or if you've ever been in a car, or on a bike, or honestly just if you've been running. It looks like everything is moving past you. It doesn't look like you're moving past it, because from your own perspective, you're never moving. So what we're doing is we're taking the way that we're thinking about the problem, and we're thinking, instead of saying like, well, the world's not moving, we think about it from the perspective of one of the objects. In order to do that, what you can do is take the velocity of the object whose perspective you want to be working from, meaning the one you don't want to be moving, and subtract that from the velocity of the other one. It's important that I'm saying velocity here. The direction's really going to matter, so make sure you include any pluses, make sure you include any minuses. When you do that, what you'll get v21 means the velocity of the second thing with respect to the first thing, meaning from the first thing's perspective, how does it look like the second thing is moving, is going to be the velocity of the second one minus the first. If it's negative, what that means is that the first object is seeing the second object move backwards, meaning that either they're getting progressively closer together, basically. Not necessarily, actually. It just means it's moving backwards. If it's moving backwards and behind them, they'll get progressively further apart. So you do actually have to be a little careful about that. All right. So taking that and actually applying it to this problem. And thankfully, we already have it all copied down. This time, my final position isn't actually going to be New York. I don't know what my final position is because sometime before New York, after I added the problem, we're going to be at the same place. So what I'm going to do is I'm going to say that my final location, I'm actually going to set up two little variable charts. One for me, one for my friend. In both cases, the position is just going to be the position that we meet up at, and I don't know it. But we have different starting positions. The starting position for me, I've named 0. The starting position for my friend is 30 miles in front of that. So I'm going to call it 30. I know that the velocity for me is equal to 70. I know that the velocity for my friend is equal to 60. I also know that the time that it takes both of us to reach that place is the same because we're starting at the same time and neither of us is stopping traveling in the middle. So I don't have to put a subscript for the ones that are the same for each of them because it's not meaningful to distinguish whether or not it's mine or my friend's if those are the same thing as each other. This is going to be the key to solving this one. Because if I look, there are two variables. There's position and there's time. I can set up two equations, one for me and one for my friend. That means I'll have the same number of variables as equations, and I can actually solve it out. So doing that, what it'll look like is that we've got our position for me, which will equal the initial position for me. Actually, that should have an initial, that should have an initial. Plus the velocity for me times the time. For my friend, it'll be very similar. There we go. First step is to solve one of these equations for one of the variables, in particular the one you want to eliminate. We're being asked for how long it takes for something to happen, so the big thing that we want to wind up with is the time. This is our final answer. So I don't want to solve for the time because that'll mean it'll take more steps because whichever one I solve for first is the one that I figure out last. So I'm going to solve for x first because we're not really being asked for it. We're not asked where we meet up with our friend. We're asked how long it takes to meet up with our friend. So what I can do, and if you have another way to do this that you like better, that's fine as well. Just as a heads up for now. What I can do is I can take x and I can replace the other x with all this stuff because they're the same thing as each other. That's what equals means. And when I do that, I'll wind up with an equation that no longer has two variables. The big problem with this first equation is that if I try to solve it for time, when I plug in numbers, I don't know x, so I'm not going to be able to get it. This is letting me figure out what x is by saying, well, x is this using the time. When I put this in here, what I'll get is that my position at the beginning plus the velocity I'm traveling at times time will need to equal my friend's position at the beginning plus the velocity my friend is traveling at times time. And what's relevant about this and why we do it is because time is now the only thing I don't know. So if I solve it for time, I'll actually get an answer because everything else is just a number. So to do that, we need to move everything with a time on it to the same side as each other and everything without a time to a different side. I'm going to move all the times to the left so that when I solve, stuff's on the left. So I'm going to subtract VF times T, subtract VF times T. That brings this time over to the left. And I'm also going to subtract my initial position, because that'll get rid of my initial position from the left because I only want things that have a time multiplier divided by them. Doing that out, we'll get that the velocity of me times time minus the velocity of my friend times time will need to be equal to the position of me at the beginning minus the velocity of my friend at the beginning. The position of my friend at the beginning. From here, we need to factor. Both of these have a time. So I can take this and pull time to the outside. And when I do that, what it'll look like is that time times the velocity of me minus the velocity of my friend will equal the position of my friend minus the position of me. And so what I can finally do to get my answer is divide each side by that velocity of me minus velocity of the friend. And we're done once we plug in. And so we've got time is equal to the position of a friend minus the position of ourselves divided by the velocity of ourselves minus the velocity of our friend. And putting in our numbers, we know that our friend's position was plus 30. We know that our position was 0. We know that our velocity was 70. And we know that our friend's velocity was 60. So we'll get 30 over 10, which is 3. So that tells us that it takes 3 hours to catch up. I do want to briefly highlight something. If you remember back to the relativity part of the slide, this is the relative velocity of you compared to your friend. This is the relative position of your friend as compared to you. So your friend starts out 30 miles ahead of you, is what this top part is saying. Every hour, you catch up by 10 miles, is what this bottom part is saying. And so if you take that 30-mile head start and you divide it by the 10 miles you catch up by each hour, that'll give you that it takes 3 hours. And if that way of conceptualizing it is easier for you, that's fine. Just be careful, because that gets harder depending on the situation. We do have one last question, which is part C. Part C is asking how long you wait for your friend at New York. But the time to wait is actually going to be the time it takes for you minus the time it takes for your friend. We have the time it takes for you. We figured out that was 6 hours. So now all we need to do is figure out the time it takes from your friend, and we can subtract those two and get our answer. The time for your friend is actually going to be very similar to the time for you, except because of that 30, we do have to actually be a little more careful with the equation. So the position for your friend is going to be equal to the initial position for your friend plus the velocity of your friend times time. If I want to solve for time, I'm going to have to subtract off the initial position for your friend. That'll give us that the position for your friend minus the initial position for your friend is equal to, or the displacement, is equal to the velocity of your friend times the time it takes them. Then we just need to divide by the velocity for your friend. And we're all set. Which is 420 divided minus 30 divided by 60, which is 390 divided by 60, which is 6.5. I did the subtraction wrong. As an aside, it's the if you're trying to figure out how long a person waits, you subtract the one that's it's presumably doing the weighting from the other. So this should be positive, this was positive. This should be negative, and this should be positive. So that'll give us -6 plus the 6.5 from our friend, which gives us half an hour that we're waiting. This one's already 25 minutes. I think I'm actually going to stop this one here and do the next example problem, which is a little trickier as a really just as a second video, as like a part B. So feel free to check that out if you want to see another example, and goodbye YouTube.